Be more valuable than the free lunch. I appreciate you spending this 1 hour with me, and hopefully I'll give you something meaningful in return. I'll talk about our work on carbon materials, and mostly those are focused on very fundamental surface chemistry, but a lot of it are related to absorption. So hopefully you'll see some relevance to the work we're doing here. Okay, before I start, I want to.
You can just use my mic.
I want to thank my students who did the work. This photos a couple years back, but most of the work are done by a couple of grad students. Thank you. Jiting, who's now doing R&D in electronics industry, and also very close collaboration with a colleague in chemical engineering, Professor Lei, and also Professor Shigeru Memiya in the chemistry department. And certainly funding from both government and the internal funding from the University of Pittsburgh. I want to start my talk with this quote from Albert Einstein. He said, "A theory is something nobody believes except the person who made it." I really use this to make joke to my theory colleagues. So they come up with things that they feel very excited and they try to fit to experimental data and that but there's another half of Albert Einstein's quote. He said, "Experiment something everybody believes except the person who made it." I think probably that's where doing the dirty work in the lab probably would appreciate this. And I especially like this because a lot of the work we do in the lab, actually, I believe is along those lines, that how intricate and how complicated some experiments really are. And if you don't have actually a good theory to guide you, a lot of times you come up with something that everybody believes except yourself. All right, so I want to start with this overview slide. A lot of the work we do started with wettability, but I want to emphasize that wetting is very much related to another very fundamental surface property of all materials, and that is surface energy. And specifically to carbon materials, especially graphitic carbon materials, think about their applications. Pretty much all their applications are related either directly or indirectly to their surface energy. If you just think about lubrication, graphite is a very good solid lubricant, and the conventional idea is this sliding mechanism. And the separation, this is huge in this room, I presume, and everything related to separation is related to absorption process, and certainly that couples to surface energy. Electrochemistry, unity storage, double layer structure, they all involve some kind of reactive chemical come to the surface or species come to the surface, and that dynamic would be impacted greatly by surface energy. And certainly composite materials, and even theoreticians like graphite, because this is a very good model system. This is one of those few materials that does not undergo surface reconstruction in air because it's chemically stable. It's all sp2 carbon stable. So this is used in a lot of modeling as a system to just test the theory and to figure out what is the best theory out there in elucidating surface properties. Now, the very simple, seemingly simple graphite-water interaction is actually pretty tricky to fully understand it at a fundamental level. And there are a couple of experimental challenges in simply understanding what is the absorption energy of one water molecule on graphite. And experimentally, it's difficult because your graphite is never going to be perfect. There's always step edge. And the step edges are, as you may expect, high surface energy area. So molecules want to stay there before they move to the basal plane. And also water like to hydrogen bond to each other. So it's just difficult to get this isolated water molecule on graphitic surface. Now, computationally, it's equally challenging because graphite itself is a highly correlated material. So it's a semi-metal. So there's an extreme electron correlation effect that you have to deal with. And certainly, there's many body effect on the same line of reason. So turns out everything can be done at microscopically very, very easily. And this turns out to be a good way for theoreticians to understand the microscopic interaction. So microscopically, we can measure contact angle. You add a drop of water or any liquid onto a solid substrate, you measure this angle. And that gives you the degree of interaction between the liquid and solid. All kinds of models has been derived. Small relationship is one of the simplest and widely used ones. But that gives you essentially the magnitude of solid-liquid interaction. So what you can do, microscopically is you can simply model a big chunk of water. When I say big chunk, I mean couple of nanometers size. Okay, and you just put it onto a piece of graphite and you change the size of the water droplet and you extrapolate to the degree of infinite size of water droplet. You can get the water contact angle. If you're doing molecular dynamic simulation, you can just tune the parameters until you find this magic combination that reproduces the experimental value. And wow, you got the molecular interaction parameter that you can use in any other molecular simulation. Okay. So that in theory works very well. That's exactly what this paper did. So for this to work, you need to have reliable experimental measurement here. Okay. That's pretty easy to do. Just add a drop of water, pull your cell phone, take a picture, just measure the angle. That's it. Okay, and that has been done many, many times. And the earliest one I can find is this paper from 1940. This is a paper from Journal of the American Chemical Society, the flagship journal in my field. Everybody would die to publish on those journals. I certainly would be one of them. But 1940, you can just take contact angle measurement on graphite and can publish there. So this is the abstract, and what it says is contact angle of pure water on this graph. This is some kind of natural graphite from South Asia. I forgot exactly where. And the contact angle varies between 85 to 86, more or less. So that fits our conventional picture that this is a nonpolar material. Nonpolar material doesn't like polar water, so it's a hydrophobic material or surface. Okay. Now, I'm talking about unfunctionalized basal plane graphite. I want to emphasize that this is not active charcoals type of situation where there's a lot of surface functionalization. This is the basal plane graphite. There's no oxygen, nothing else, just carbon. So this kind of measurement has been repeated many, many times. A lot of different materials. This is the original 1940 research. And after that, there are all kinds of carbons being measured, HOPG, aged HOPG or graphene, and with one exception. This guy, Schrader, in 1978, he did a very interesting experiment. He measured the wettability of graphite in ultra-high vacuum. And this is a very controversial experiment because water evaporates in vacuum. And when he did the measurement, he broke the vacuum in a UHV chamber, introduced water vapor, condensed water vapor into water droplet, put it onto graphite. You got a very low angle. Nobody likes this angle because obviously it's different from the rest, large angles. And people think, oh, you have low pressure, water evaporates, and that leads to a reduced contact angle. That sort of makes sense. So this paper has been published for many years, but has not been widely recognized. If you open any more recent papers or books, and chances are you're going to see graphitic carbon being a hydrophobic material instead of hydrophilic material. So the goal of my talk today is to convince you that all those numbers are wrong. In particular, those big numbers, those 85, 90, those numbers, pretty sure they're wrong. Okay. I think this 35 is also wrong. I'm not so confident. Hopefully, I'll convince you that those 85, 60 numbers are 86 numbers are terribly wrong. And why they're wrong, I think, goes back to Albert Einstein. Is the kind of experiments that only the people doing experiments know they are wrong, and not having confidence, and everybody else feels pretty good about them. Okay. All right. So this story started when I joined Pitt. And at that time, graphene was in fashion, and I was interested in studying surface chemistry of graphene. So we have a lab process to grow graphene. This is a process that has been very well established. What you see here is a copper foil. We heat it to 1,000 degrees Celsius. We flow methane gas. There's a catalytic process happening on the surface of copper, self-limited, so you end up with monolayer graphene. This is very well established. There's Raman spectrum shows a single layer, all kinds of things that just very reliable. So the story goes, I have a bunch of undergrad students in my lab, and the reliable verification of single layer nature of graphene is through this Raman process, which requires laser, which is dangerous. Why? Because you have two chances of making mistakes when you use laser. The first chance, you blind your one eye. The second chance, you blind either. Okay, so that's not good thing for my undergrad students to do. So we thought, oh, what about wettability measurement? That's simple. They can use their iPhone. I don't even have to supply any equipment, right? So there goes. I have a bunch of undergrad students measuring content of graphene. Now they came back saying, Professor, this is terrible. We can never get consistent data. Sometimes the numbers are 86, 90, which is the literature data. Some other times it's like 40. It goes everywhere. We don't know why. And usually the response from advisor to their student is something wrong with you, right? Repeat, figure out why. But very quickly it becomes very clear to me and my collaborator that the only thing that is reproducible is that it's not reproducible. So, and it turns out all the graphene are good. So our process actually is very reliable to the point we actually don't need all this characterization to verify its monolayer. So we got curious and eventually figured out why. So this is probably the most important piece of data. I want you to focus on this one. This is the contango data we measured on graphene, and the graphene pieces are this large. Okay, so we can add a lot of water droplets. X-axis is time, and time zero is defined by the time when we take the sample out of the CVD chamber. In CVD chamber, there are under argon, hydrogen, and methane high purity gas. We cool the chamber to room temperature, take it out, we start timer, and we add water droplets sequentially, and we measure content. And you see there are 6 different samples. The same trend emerged that initially the content was very low, around 40, 50-ish. Within about 10 minutes, it goes to about 60-ish. Okay. Now, this is not a temperature effect, I want to emphasize. Okay. It's not a temperature effect. On the right-hand side, I show measurement plotted in different way, 10 different samples, more or less. And the time zero, you see a cluster around 40-ish. And the time 1 hour, you see about 65, 70-ish. And after 1 day of exposure in air, we got content around 85 to 90. Now, 85 to 90, as you may recall from the table, that's the magical literature data of wettability of graphitic material, including graphene. So this is the literature, and we can reproduce the literature. But seeing this trend, it's pretty clear that this is more likely the intrinsic behavior of the graphitic surface. Okay, specifically the graphene on copper material. So the next question is, what is happening? And turns out is the air. So what you see here on the left is the ATR FTIR spectrum. This is sort of a little bit surface sensitive FTIR technique. What you see here is the CH2 vibration peaks, symmetrical, anti-symmetrical peaks, and also there's a shoulder that looks like it's a CH3 peak. Okay. So their intensity grows over time. And on the right side is the X-ray photoelectron spectroscopy, XPS, that probes the surface elemental composition. This is very surface sensitive. Now, our sample is graphene on copper, so there's naturally a layer of carbon, but also you see this is a carbon peak to add. The black one is the new sample, and the red one is after a couple of days in air. So there's additional carbon on the surface. Here I want to emphasize XPS is done in ultra vacuum. So a lot of things would desorb, but even that, you see this additional carbon accumulating on the surface. So with this, it's pretty clear to us that there's organic materials on the surface. And the hypothesis there is that this organic coating from air changes the wettability of graphitic carbon. So I teach physical chemistry at Pitt, and this turns out to be a very good physical chemistry problem for gas kinetics analysis. So if you make a very simple model, 1 atmosphere pressure, room temperature, assuming the sticky coefficient, which is the likelihood of the molecule, after they strike the surface, are they going to go away or not? We're just going to assume if they strike, they're never going to go away. Okay. With that assumption, you can calculate how much time it's going to take to form a monolayer amount of material on the surface. And that's about a couple of seconds if you have parts per billion level of contamination in air. It would be a couple of hours if it's parts per trillion level of contamination in the air. So translate that into real life plasticizer emission from vinyl floor in this room, for example. That's about parts per billion level. If you close the door, let the carpet does this thing, because the molecule is going to evaporate. And that steady state concentration measured by mass spectrometry is about parts per billion. So that takes a couple of days to establish. Okay. Pump oil, the best pump oil give you a partial pressure of parts per trillion level at room temperature. So our kinetic profile is somewhere on the order of hours. So that fits this kind of overall picture here. All right, so that's what we measured on. Oh, by the way, feel free to stop me with any questions. Be happy to have a real-time discussion. So that's measured on graphene, on copper. I want to emphasize that the material is not graphite; it's a single-layer graphite, but with a copper substrate. Okay, and why I want to emphasize that because that copper substrate turns out to be important because for a lot of surface interactions, the interaction is long range. Think about van der Waals interaction. Think about charge-charge interaction. If you have very thin coating on the surface, the molecule sitting on that copper graphene substrate can actually feel what's beneath graphene. Because graphene is only 0.3 nanometer, and van der Waals interaction can extend to nanometer range. Okay, so we can do the same experiment on graphite. This is the HOPG artificial graphite, and the data will be slightly different, but the trend is the same. So on the left, I show two measurements plotted in one graph. The dots are contango measurements, and this is the contango value of graphite. And graphite is exfoliated by using Scotch tape. So you have a clean surface. We start the timer after exfoliation. And we just run the experiments in air. We see the steady growth of contango. Now, the initial contango data is not 40 anymore. Now it's about 60. It goes to about 80-ish. Remember, that's the magic experimental value reported in the literature. It's more or less linear and then plateaus. On the same sample, we can also do ellipsometry, and this measurement can essentially give an average thickness of surface coating. This is done by using a laser, shooting the surface, looking at the change of polarization and the intensity of the refractory light. And this gives you the grain line, and you see it's a more or less linear growth process, and it saturates to about 0.5 nanometer surface coating. So lithography doesn't really tell you what kind of materials on the surface, and it's heavily model-based. You get this change in polarization, and you fit into a mathematical model, assume that it is organic molecule. That's the assumption we make. But with that assumption, we got about monolayer coating on the surface, which more or less makes sense. Okay. With FTIR, we also observe similar things. With the fractionally exfoliated graphite, we see this flat line. After a couple of days in air, we start to see this very noticeable dip in the FTIR. Those correspond to the H2 vibration. So again, you see this surface absorption of stuff, organic stuff from air to the surface. More recently, we started to look at the spatial distribution. This is an interesting experiment where we have this graphite exfoliated again, and we use a technique called surface potential measurement. This is the AFM atomic force microscopy technique where it detects the surface potential. So essentially, that's the voltage, the potential of the surface, and you can do a surface mapping. And I showed 3 different maps. Those 3 maps are actually on the same area. Those are not topography, but rather the surface potential map. And the scale bar here is 10 micrometer. So those are relatively large area. But what you see here is rather striking. Initially, you see a more or less homogeneous surface. After a couple of days of exposure in air, you start to see this heterogeneous complexity showing up on the surface in the surface potential map. And those surface potential are sensitive to the surface absorption of molecules. Just imagine you have polar molecule, whether the dipole points in this way or in this way, that will directly change the surface potential detected by the FM tip. But after another couple of days, the surface becomes more homogeneous. So you start to see this kind of bell curve, and especially the feature size are a couple of micrometer. So the take-home message here is there's this absorption of all kinds of molecules from air. We don't know exactly what they are. But the absorption is not homogeneous on the surface. It goes through some kind of domain process. But eventually, it becomes homogeneous again. So it appears to be some kind of dynamic replacement, which is not really surprising. And the model I have in my mind is you expose your surface to air, the small molecular weight stuff come to the surface because they're fast. They're high concentration. But they're eventually replaced by high molecular weight species that has, thermodynamic advantage because they're high molecular weight. And they eventually come in and kick out the smaller things. So that's the model in my mind. So with all this in mind, we look at numbers. So here I want to share some surface energy measurement we did on graphite, graphene and copper. We also did similar measurement on graphite, but the message here would be similar. Those are done by doing contango measurement on clean graphene and contaminated graphene using different testing liquids. So I showed data using water. We also did diethylmethane and ethylene glycol, glass rope. But using all this contango data, we can put into a model, and the model will give us the surface energy of graphene and copper. And that is the data here. So, so the particular model we use, the Folks model, which actually is the guy who published the 1940 paper. That's the same Folks. He's a big name in biology. And so he has this model that splits surface energy of solid material into 2 components, the nonpolar component and polar component. So the way to think about this is surface interact with liquid in 2 different mechanisms, the polar interaction and nonpolar interaction. Nonpolar would be van der Waals interaction. Polar interaction would be hydrogen bonding, charge, induced charge interaction, things like this. So if you look at this 24-hour sample, this is the sample that has been contaminated by air. And what you see is most surface energy coming from the non-polar components. The polar components are more or less zero. Okay. And that fits our conventional idea about graphite or graphene, because that's a non-polar material. Right? But if you look at the freshly prepared sample, there's actually a sizable polar component in it. Certainly the non-polar part is also bigger. So there's about 25% reduction in the surface energy due to surface contamination. Now, what is this? We're not 100% sure, but the current hypothesis we want to test is that this is coming from pi hydrogen bonding. You have large pi system in the graphitic material, and that can serve as a hydrogen bonding donor, acceptor. So proton being positive charged interact with electron-rich pi system. Now, before I move to the properties, I want to emphasize that this is actually nothing new. We were very excited that we discovered something interesting, but realizing this is very common is nothing to be excited about. So it happens everywhere. We did a similar experiments on aluminum disulfide, another 2D material. And here on the left, I show the FTIR. You see the same CH2 vibrations picking in on the surface. On the right-hand side are ellipsometry measurement, 5 different samples. You see the same kind of feature of linear growth and saturated around 0.5 nanometer. And there's some interesting time dependence here. So if you look at this one is much slower, right? And this one is in spring. And a bunch of those are sort of in the fall and winter. My hypothesis is it's raining this day and not raining in the other days. Unfortunately, we didn't have the data to back that up. Okay. It's also we also see the same thing happening on metallic substrate. This is a recent work we did on porous gold material, where this is a very popular surface enhanced Raman scattering substrate, SURS, a very popular, important, widely used analytical technique. What we did here is we made this SURS substrate, which is this porous gold. We just leave it in air. Didn't do anything. We didn't put any analyte on it. Just leave it in air. We start to use SURS to scan the surface. And interestingly, or not surprisingly, we start to see all kinds of peaks showing up on the SURS substrate that supposedly is nothing on it, but it's getting stuff from air. A lot of those peaks can be assigned, and one of those components seems to be related to amorphous carbon. And here I show one of those clusters. So this is a frequency and the peak intensity of this 1585 peak that's very close to one of the signature peaks of amorphous carbon. Initially, we don't see a lot of high intensity spot, but after 5 days of exposure in lab air, we start to see a lot more high intensity locations, suggesting there's a capturing or presence of amorphous carbon material on the surface. But certainly you see other molecular features like this one, for example, is another feature suggesting the presence of long chain carboxylic acid, and there are many other things going on. But the bottom line is, even for analytical technique that is highly sensitive, you don't need to do anything to capture things in air. And a lot of those signals in the literature actually were thought to be single molecular events detected by SURS mechanism. Now, outside our lab, there are other observations of similar behavior, but unfortunately not assigned to the correct mechanism. So this is a paper published by a group from MIT, where they made a very exciting discovery. We find there's all rare earth oxides are intrinsically hydrophobic. There's a lot of industrial relevance here because hydrophobic coating is super important in heat exchangers. You want your heat exchanger surface to be hydrophobic so that water droplet can go away. And especially you want this coating to be robust. So we have an oxide material that is intrinsically hydrophobic. That's very exciting. Yeah. And they have their data showing that it is, 110 degree water content go on their oxide materials. But we look at this, being a chemist, all this doesn't make any chemical sense because you have ceramic material, you have oxide, you have metal ion. It should be hydrophilic because this is a charged surface. Right? Now, what we find is this is essentially another case of surface contamination. You have we made samples, rare earth oxide samples, and we can reproduce their hydrophobic behavior, except after we heat the sample in air to oxidize the surface at high temperature, we no longer see this hydrophobic behavior. Instead, it becomes super hydrophilic. And there are actually a lot more other examples in the literature where people observe this very interesting hydrophobic behavior and think, oh, this is exciting. But in fact, it's simply because their lab air is dirty. So going back to the motivation page, at this stage, we figure out that there's this wettability measurement has been terribly wrong since 1940. So for about 70 years, people are publishing reproducible data that matches this 85, 86 degree number in the literature. Everybody's happy. So it's self-propelled purposely there. But if the wettability measurement, which is simple to do, right, and widely done, has been masked by this airborne hydrocarbon contamination, naturally you want to ask the question, what other measurements has been impacted, but we just don't know. Okay. So thinking about all this landscape, we think about lubrication. Graphite is a very good solid lubricant. And I was so convinced about the sliding mechanism until I was told that graphite works very well on Earth, but doesn't work in satellite. Graphite increases wear in satellite setting in outer space. Okay. So that says a lot about the other side of the sliding mechanism. Certainly, there's a lot of interesting research I think can be done looking at the absorption. Now, what we focus in recent years are more on the electrochemistry side. We look at how this impacts electrochemistry, how this impacts energy storage, and this would relate to the electron transfer across the heterogeneous interface and also the double layer structure, and both could be impacted by the presence of additional coating. And by the way, so this theory fittings, they used to fit to 85 and 86. Now they fit to 64, which makes me uncomfortable because I'm not sure if that number can be changed someday, right? So there are other people reproducing the 64, but you never know what's going to happen there. So on the electrochemistry side, this turns out to be another very interesting controversy. The basal plane of graphite is a very good monosystem, as I said, not only in surface science, but also in electrochemistry. In the 1980s, there's a huge amount of work done, basically concluding that the basal plane of graphite is not good. The electron transfer is very slow, very sluggish, just not good electrode. On the other hand, the edge plane is good. And their explanation was the basal plane lacks absorption sites, so that's just not good for electrochemistry. Until in early 2010-ish, there's a group of people, they started to publish, look at the title, Definitive Evidence for Fast Electron Transfer on Basal Plane. Okay. So these two people fight each other. There's actually a conference designated for this two group of people so they can fight each other. I really wanted to go, but I couldn't. Anyway, we look at this and we realize this might be another example of two groups of people doing the same experiment, but do it in a slightly different way and maybe work on different kind of sample in reality. Okay. So we did a very simple experiment where we exfoliate a piece of graphite and use that as an electrode to do a Ryan ipsometry. If you're not electrochemist, don't worry. So you look at this voltage of potential, current versus potential. So you change the potential, you look what kind of current you collect on the electrode. The higher usually is better. That means your electron transfer is faster. So what you see here is you have a graphite freshly exfoliated. The current is high, and you leave in the air for a different amount of time, the current goes down. Okay, very simple. And that simply shows the surface cleanness is an important factor. And having a layer of essentially oil, non-conductive oil, would force the electron to tunnel through this additional half nanometer. Remember that half nanometer. And that would exponentially reduce the electron transfer rate kinetics. I'm going to skip this one. We also look at the absorption process in water. So this shouldn't be a surprise to everybody here. We look at the ipsometry measurement. We can also do it in water. So this is the thickness of coating on graphite, but immersed in water. And x-axis is time. So we use the ipsometry to monitor the absorption process in real time. And we have 4 different samples, and all of them show some kind of buildup of add layer. Now this is done in nanopure water. Supposedly in academia, that's the best water we can have in the lab. By the way, filtered by a charcoal filter as part of it. But still, you see this buildup of half nanometer thin, and that plateaus. On the right-hand side, it's the same kind of experiment, except the liquid phase is sodium chloride electrolyte, and it's just regular sodium chloride from Sigma Aldrich, and you see this dramatic increase in the kind of stuff on the surface, going all the way to about 2 nanometer. So with this in mind, we look at how this would impact the double layer structure, and we measure the double layer capacitance of graphite. This is the capacitance as a function of air exposure time. Each dot is a separate experiment, separate sample of graphite, separate exfoliation. So we exfoliate graphite, leaving air for a different amount of time, measure the double layer capacitance. That's the reason for large variation here. But the big picture here is you see this about 50% reduction in the double layer capacitance. So having that half nanometer of oil would significantly reduce the double layer capacitance, and by that, the energy storage capacity of carbon-based capacitors. On the right-hand side is a same kind of experiment, except everything is done in liquid phase on one sample. So we continuously measure the double layer capacitance of one carbon electrode. So this is a continuous measurement. And at a certain point, we stop the experiment. We start to apply a high or low potential with the thinking that maybe we can drive off the surface contamination. In a sense, can we recycle the material to make them clean again? And you can see this is where we stopped. So we can either do very low potential or very high potential. And in both cases, we see this temporary increase in the capacitance, which suggests that the contaminants has been driven away, at least partially. Okay? But it's not a permanent solution because the environment is dirty, so it goes back being contaminated. We can do this repeatedly and showing some repellent effect or self-cleaning effect on the surface. So with this data, we start to just make a device and look at a real capacitor, because the real supercapacitor does not use a graphitic carbon. They use active carbon high surface area, and a lot of those surfaces are functionalized. So we do the same kind of measurement. We do air exposure, and we measure the capacitance, but this time we do it on the highly porous active carbon material. So interestingly, if we do the exposure in air, there's actually not any downside. There's actually a slight increase in the capacitance. But if we do it in glove box, dry environments, there's about 20% reduction. Now, how do you understand this? It's not too surprising to us, because on the active carbon material, the surface is actually hydrophilic. you can actually bring in water, and the water absorption competes with hydrocarbon absorption in air. And that wetting, the initial wetting, prevents fills the pore and prevents the eventual contamination. But that mechanism does not happen in a dry environment. Okay. On the right-hand side is the charging discharging curve we conducted on active supercapacitor we built, and with intentional exposure to toluene vapor. The message there is pretty simple. The longer exposure to organic vapor, you start to see this reduction in the charging discharging curve. Okay. So the larger the cycle, the better. All right. So along the same line, the last relevant experiment we did is to look at the electrical conductance. And this is just looking at current flow through a junction. Why that's relevant? Because carbon materials is very relevant in MEMS, microelectronic, micromechanical system devices. Those are small, very small mechanical parts and very small electric contacts, and we're interested in how the surface contaminant impacts the electrical conductance. And this is a dry contact, essentially, in air. So what we did is we use a conductive FM atomic force microscope setup. We have a tip, we have a graphite substrate, we apply voltage, we measure the current. Okay. And the results are in the middle, and the message is pretty simple. When you have clean surface, you see this immediate saturation of current, so good conductance. And the longer exposure or sample in air, you start to see this reduction in the current. So as you would expect, once you have organic coating on the surface, the conductance, electroconductance goes down, and that's what you expect when there's a layer of oil on the surface. So I think with that, I want to conclude with the hope that I convince you that graphitic surfaces are more hydrophilic than you think. I want to emphasize that it is not a super hydrophilic surface by any standard. Contact angle of 60 in the case of graphite is not super hydrophilic, okay, but it's more hydrophilic than people used to think. Hope I convince you that there's airborne hydrocarbon everywhere, and there's probably a bigger market for this company than you think. But you probably know this already at the same time. So there are many surface properties of carbon materials, and I want to add many other materials that are potentially being modified by this contamination. I have to emphasize this process can be really fast. For small molecules, small organic molecules, it only takes a couple of seconds to create a surface coating. So there's this hope in my mind that there's this another paradigm of carbon material. If we find a way to maintain a clean environment, maybe you can find a different carbon material that is, more conductive, just better in every aspect. Okay. But the question there is always, how are you going to maintain a clean environment? Or maybe you don't have to, but how do you momentarily maintain a clean environment so that you can use and utilize that unique property, the intrinsic property of carbon materials? So I'll stop there. And again, thank you for attention. Thank you for thanks to ACS local chapter for hosting this, and Calgon Carbon for everything. That's my appreciation.
Thank you.
I'd be happy to entertain any questions.
Is it just at a certain time afterwards, or are you back calculating based on time to like a time zero? Based on
Yeah, good question. So experimentally we do for the graphic exfoliation, we do exfoliation, we immediately measure that this 5 seconds delay, for example. Okay. Now, if you trust the ellipsometry measurement, if you look at the ellipsometry measurement, it's reasonably linear. Okay, and if you do extrapolation, we're not going to be too far away from the first data point. Yeah. So we did not do extrapolation. We'd rather use the time zero, which is more or less 5 seconds or so. We use that number.
So a really interesting talk, which brings to mind a number of thoughts. One of which you already put on the page for me. That is, I think you make a compelling case that maybe every room in the world should have an air filter with activated carbon in it. But secondly, honestly, your talk is kind of unsettling, right? I mean, how many millions of measurements get made where the researcher assumes there's a clean surface and there isn't one? How are you thinking about how to find specific areas, for examples where you should bring these results to other researchers and their past results and say, hey, have another look?
Yeah, so from a fundamental research perspective, there are two ways to think about this. One is, do we really care? I mean, we've been using carbon many years. We've been using the model, not knowing there's a layer of coating, but the model would phenomenologically incorporate that effect, right? So if you're for people doing, let's say thermodynamic modeling, for example, that parameter would incorporate the effect of surface coating, contamination layer in it.
Unknowingly.
Unknowingly, exactly. So if the experiments are all done in air, and if the process does not involve the intrinsic presence of the surface coating, maybe it doesn't matter at all. Now, in other cases, maybe it does not. For example, if you want to understand the sensing response of a carbon-based sensor, now having that coating and not having that coating would be different, because in one case, analyte come to a surface, immediately produce the effect, and in another case, analyte come to a surface and replace the surface coating, and the sensor response would be very different. Again, phenomenologically, you can create a model just assuming that the sticking coefficient is different, right? So if we have that kind of thinking, party goes on, and I don't see a big problem. Now, certainly that would limit our understanding in many other areas. For example, in the case of SIRS, we show that a lot of those so-called single molecular events are likely coming from contamination. Even if people claim they reduce the analyte concentration to, picomolar range, or doesn't matter how low, maybe the environment's so dirty to begin with that whatever they measured is not actually coming from the analyte. So I do see a lot of, value there. But that's a good thing for me as an academia, because I have a job to do. So I don't find it unsettling.
Could you go back to, I think, slide 24? So on the case on the left, A, what's building up there?
Good question. So as I said, this is done in nanopure water. This is done in a glass container. What is building up there? It's hard to say. Could be, I'm thinking a couple possibilities. Doesn't matter how careful we are with the glassware. There could be soap from cleaning the glassware. There is the possibility of air contaminant coming from air absorbed into water, transport to the graphitic surface. The kinetics there is much slower than the air case, and it could be a lot of things. And certainly it's very deep, but if you look at the sodium chloride side, that seems to suggest very strongly that it's a real thing. It's not, for example, a surface oxidation or water intercalation or something. Yeah, at one point we thought about intercalation of water underneath graphene, but the sodium chloride experiment showed that's probably not the case.
If clean room situation, you have different classes of clean room. If you ever looked at, say, I forget the exact class 10, class 100, whatever they are. Like if you ever looked at the effect as a function of the class of clean room.
Yeah, so
that's
I've mentioned this, clean room is not clean.
yeah, right.
Clean room is clean in the sense of particular matter, but clean room is actually very dirty in terms of hydrocarbon.
Okay.
Because this is a closed environment. Air cycles back and forth, and people wear a lot. There are a lot of chemicals. When I say chemicals, I mean rubber, plastics. You know, even I'll give you one extreme example. We did experiment where we have two pieces of graphene. We place one, both made fresh. We place one in the plastic petri dish, another one in the polystyrene petri dish, that's standard then from BWR, whatever avenue you use. And we measure the contact angle. The one we place in polystyrene petri dish goes up faster in contact angle. Yeah.
Sort of a question for Calgon carbon. I wonder whose applications that Calgon carbon has. Do they arrive at the appropriate type of carbon to be used by an empirical method of just poking around and finding what works? Or are there predictive models that are based on surface chemistry and absorption, isotherms, and those kinds of things?
I thank you on behalf of my theory colleagues.
Yes, we do have some model. We do have our own model. We can, based on both theory and years, maybe 50 decades, 70 decades, 50 decades of experience, right? 5 of 50 Here is the experiment data. So we have our own model, can predict that absorption performance.
If my own experience, I'm ever using isotherms.
After some,
predict
yes.
When absorption columns are saturated and when they need to be regenerated, for example. You see any of this work modifying those isotherms? Or is the organic absorption on the activated carbon surfaces a necessary evil up with which we have to put?
Can you repeat your question again?
Yeah, that was Winston Churchill, sorry. Do you see these kinds of contaminations, pre-contaminations of activated charcoal surfaces as requiring any adjustment to your isotherms? Or you kind of figure that you have to put up with these contaminations and they're always going to be there, and isotherms work pretty well. You know, maybe in the future your columns could get smaller or more efficient, or sort of wonder.
Okay, so how our model work is we have clean virgin carbon, no contamination, and we know if the customer provide us, say, okay, we have this stream air or water, have the contamination, and the concentration level, then we can do prediction. If it's like huge carbon, if any already pre-absorption and which is unknown to us, then you will see the model prediction will be different to reality. Yeah.
So I also want to emphasize that everything we did here are on unmodified graphitic carbon. Active charcoal is very different. I'm not even sure you should worry about it. Well, maybe you should worry about it. I think that's good as well.
So I have a question. So about airborne or other waterborne. So you mentioned this hydrocarbon, specific hydrocarbon. How about other contaminant, which is non-hydrocarbon?
Yeah, so we see evidence of, as I said, active charcoal, active carbon, amorphous carbon material depositing. We almost So, in the case of the SIRS experiment, it sounds as if there's amorphous carbon particle floating in air depositing on those surfaces. I don't know exactly where they come from. Might be coming from the tires, being rolling on the highway, and there's carbon additive that's floating in air, and it goes all the way into chemistry department. But we see those very strong signatures of amorphous carbon. And when we add a filter that is never going to be able to filter molecular species, but be able to filter particles, when we use this filter to cover the substrates, we see this dramatic reduction in those Raman signatures. So it seems to suggest there's a particular matter onto the surface, in addition to molecular material. Other than that, we have done ultraviolet photoelectron spectroscopy technique to look at species. It's very complex. That's what I can tell you. We are planning to do atmospheric ionization mass spectrometry experiments soon. Hopefully, we have a new colleague coming in, having that expertise. That will allow us to directly measure the molecular species on the surface. So hopefully, I'll have more answer to you in about half a year of time.
So you mentioned all the contaminations, the interaction with the surface. Is that pure like physics absorption types, or
We
can
believe-
absorb any?
Yeah, we believe in the case of graphitic carbon, it's a phase absorption.
Okay.
Yeah, we can remove a significant portion of them by treating the surface at ultra high vacuum environment.
Okay. So when you do the contact angle, like you have time from 0 to 30 minutes, 60 minutes.
Mm-hmm.
Have you done like after 6 minutes, like evacuate, try to clean
Yes.
it and go
Yes.
back and see?
We have done those after high vacuum evacuation. You see this reduction in
Mhm.
contact angle, but it's never going to be complete because we think there are molecular species in air that are supersaturated to begin with, to the point they will deposit onto any surface. Doesn't matter what their surface energy is. You may wonder why they would be supersaturated. One model I can propose is you could have a volatile organic compound, let's say, the yummy flower smell or whatever lunch smell, and then they come into air and their vapor pressure is high, and then suddenly they got oxidized by ozone, they become polar, they become supersaturated, and they will thermodynamically they will deposit onto anything as long as they can find the surface. They will deposit, but those materials we cannot get rid of them. But there's no evidence suggesting chem absorption at this stage. The graphitic surface is chemically stable, and we don't expect chem absorption.
Any other questions? So go back to the contact angle. You have 64, 86, and 35. So what is the conclusion for the 35? What happened with it?
I'm comfortable saying that 86 is wrong. I'm not 100% sure if 60 degree is correct. I'm not 100% sure that 35 is too low. I think it's probably too low because based on our measurements, the extrapolation, we have reasonable confidence to say that even if you do extrapolation, it's not going to go to 35. So there might be a water evaporation effect in the original, in the 1978 experiment. Now, having said that, we are doing the experiment in air. There is huge amount of low molecular weight species in air, in addition to water, but things like toluene or benzene level organic compounds that come to drinks is very high. And we have evidence seeing that the surface absorption by using UPS established very quickly in air within seconds. So the submission measurement may not give us the whole picture. I don't want to leave your impression that this is all well understood. Won't surprise me at all if another paper showing that this 60-degree data is wrong and terribly wrong. I'd be happy to see that. But I guess the take-home message is a lot of things in air, and your experiments will be impacted by it. In most cases, it's fine. You know, your material is going to be using air anyway, right? So whatever measurement you do in air makes sense. But there are cases where you actually want to know the intrinsic behavior, and it's incredibly difficult to do measurement related to water and electrochemistry on the ultra clean surface. That's the fundamental limit we're facing. But that also says maybe this doesn't matter at all because you're never going to make the surface clean. Why don't just study the dirty surface?
So this will also impact like a polymer because contact angle. This is very like a well-established method.
Yeah. So contact angle polymer is known to depend on. So think about a polymer having hydrophilic, hydrophobic components. So there are plenty of research showing that if your environment is hydrophilic, then the hydrophilic part of the polymer will come to the surface in response to the hydrophilic environment. If your environment is hydrophobic, then the hydrophobic portion will come to the surface. So you don't even have to design anything special. You just, as long as the polymer is flexible enough, mobile enough, it will respond to the environment. And certainly I won't be surprised if there's absorption happening on this polymer as well.
Do we have questions from online audience? Other questions? Oh.
So we're talking about whether this is useful or not. You mentioned that graphene in space isn't a lubricant. Is that because you're using it outside of the vacuum, so therefore it never gets that hydrocarbon monolayer that allows it to be more slippery?
Yeah, I'm not claiming it's a hydrocarbon but the bottom line is when you create a new surface in graphite, this is a high energy process, right? You create a new surface, you need energy input. If the surface is passivated by something, maybe hydrocarbon, maybe something else, that process will compensate for the energy penalty. So there are experiments have been done where you have graphite column, use FM tip to push it in vacuum, ultra vacuum. It will slide, and then you release the FM tip, the column will come back. So my model is that if you see in outer space, the apparent surface energy of graphite suddenly becomes higher than the surface energy would measure on Earth, and that directly impacts the sliding. It's less likely to slide in ultra vacuum environment, and that make it less
So
likely.
this is an environment outside the spaceship versus inside the spaceship.
I'm talking about satellite, which is
Okay.
all vacuum. Yeah, if it's in a space station, that's a different story. Then everything would be normal. Yeah. On the other hand, aluminum disulfide works better in vacuum. So.
Any other question? We have a last question. If not, let's thank our speaker again. Thank you.
Thank you.
We will have a lab tour if you are interested. My colleague, Mike Love, the senior group leader of our carbon application group, he will give us a tour of the lab. Okay. Thank you everyone for joining the lecture. And then
But I don't want to be friends with you guys.
They later.